Hello everyone, I'm Maryam from University of Florida, and I have to say that I'm so glad that I've got the opportunity to present my study in front of professionals. Thank you so much for listening.
Hello everybody, hope you're doing well and staying safe. My name is Mahya. I'm a PhD student in construction management at the University of Florida.
Today we are presenting our paper which is called The Impact of Louver Geometry of Windows on Cross Ventilation in a Generic Isolated Building by using Computational Fluid Dynamic CFD simulation. During our presentation, we will go through some parts such as introduction, history, computer simulation, which I can say methodology, result, and discussion.
First part of this study is the introduction to the basic problems. In this section, general ideas related to topics are presented. We can explain the significance of this study in three parts. First, thermal comfort. Natural ventilation can improve building thermal performance by expanding the occupant comfort zone. This should be readily applicable to hot, dry climates, but is generally not an acceptable solution in humid climates. HVAC systems consume 68% of the total energy used in commercial and residential buildings. Natural ventilation is the most energy-efficient strategy for controlling indoor air quality, costing approximately 40% less than mechanical ventilation. And wind not only can produce electricity, but also can save it. Studies have shown that natural ventilation reduces fossil fuel consumption because it is a passive system that doesn't require electrical energy. These studies have also focused on vernacular architecture, especially in hot and dry climates that utilize natural ventilation for ventilation, cooling, and heating. This psychrometric chart for Lubbock weather, which our case study was there, displays that natural ventilation in summer dramatically would enhance the area of comfort zone for occupants. Before going to the next part, it needs to explain some definitions such as velocity magnitude. Generally, velocity is a vector with both magnitude and direction. The pure magnitude of velocity is speed. Navier-Stokes equation is the foundation of calculation in CFD, and vector line is a velocity vector that shows direction and magnitude of velocity. In the next part, the history and background of research are presented to indicate the reason for selecting the variables and inputs. We have lots of research about computational fluid dynamic software, which we can call it CFD. From 1990, some researchers simulated airflow in single-sided rooms by CFD. Some worked on a room with single-sided natural ventilation to find efficient depth of fresh air. Later, they understand that airflow rate would increase by enlarging the opening width. The scholars demonstrate that the louver angle 30° and 45° have the most internal speeds. The other researchers found that students feel more comfortable in a classroom with good ventilation by simulation. They understand that if the roof angle changes from 90 to 30 degrees, it will change the angle of outgoing wind from up to down. And finally, they demonstrate that if the roof angle changes from 90 to 30 degrees, it will change the angle of outgoing wind from up to down. Next part of our literature is about classrooms. Researchers demonstrate that good environment and comfortable place would enhance teaching and learning ability. Classroom is considered as a crowded area. Hence, it is more likely to increase disease such as allergy and asthma. A research described an effective opening placement and louver direction would be possible to apply efficient natural ventilation without distracting in a classroom. This research determined a representative classroom with 25 by 21 by 12 feet as a model based on the minimum applicable size of classroom for 22 students in open space schools and a low energy school building in Germany. Also, based on some standards, the upper side or the inhabitant part of the classroom is the best location for the wind movement because of avoiding paper distraction.
The next section is computer simulation, or we can say methodology. I'm going to start with a very basic process of CFD. The first one is modeling initial geometry by AutoCAD environment. The next one, defining a boundary condition for a model. The third one, generating volume mesh to have a modular output. Finding CFD solution, and post-processing to view results. The basic model in this study is a room with 21, 27, and 12-foot dimension. Based on the literature, a minimum applicable size classroom for 2020 student with open space configuration was selected as a standard model. The choice of window dimensions relied upon the previous research. Based on previous research, the computational domain is designed and reduced in scale to accurately simulate wind tunnel geometry. However, the height of the domain has been reduced to 1/3 of the room height to limit development of unintended streamwise gradient. The dimensions of the domain are 70, 240, and 15 feet in full scale, which will reduce the scale of simulation. This study has two different variables for simulation. The first is wind direction. The second is louver geometry. Concerning direction, 5 windward options are used to evaluate performance of a generic isolated building. The second variable of louver design makes use of 5 geometries correlative to wind direction. Having set all the proper parameters, finding can now be presented. Figure represents all simulation indicating airflow direction in the section. Also, it shows results related to louver variables. East and west outlets of all models show an approximate number of 100 inch per second to 160 inch per second air velocity, relatively. In fact, the building led the most pressure to both sides and passed approximately 1/5 through the window. On the other hand, indoor air velocity shows the significant difference between east and west side. West side has the higher airflow rate compared to the east side. Light blue background in the east part shows a number of 30 inch per second in the inner section. However, velocity in the west side is approximately around 20 inch per second. Having presented findings, comparison is necessary. This figure clearly displays the difference between velocity and wind vectors. Based on the literature review and background studies, a magnitude of 70 inch per second has the best impact when directing wind through an indoor space. In fact, ASHRAE states that 7 inch per second to 78 inch per second is the optimal range of indoor air velocity. And again, I have to say that it would be better to keep the higher velocity on the upper side of the room. It must be noted that maximum flow would be acceptable when occupants have no direct control on their environment. Vectors move throughout entire rooms in predictable patterns and increase indoor velocity. In the interest of further comparison, this table demonstrates that 75° creates optimum velocity. This table diagrams that 113 and 68° have the same amount of magnitude in the habitable or sitting portion of the room. Overall, it can be deducted that non-dimensional indoor average velocity, especially for the sitting area, shows only a small difference. Having presented findings, comparison is likewise necessary to the second variable. This figure catalogs all results related to non-dimensional velocity and vectors. It is clear that T2, D1, and D2 increase indoor velocity significantly. However, velocity around inlets is higher than the preferable amount. Model T1 directs wind to the non-habitable section of the room. Thus, the T1 option would be the best choice for the classroom. Also, if the angle of D2 were to increase to 35°, results would show more similarity with T1. Again, in the interest of further comparison, Table 2 demonstrates that D2 has the highest velocity average in the entire room. This table provides that I1 and D2 have the same magnitude in the sitting area. Despite the assumption of aerodynamic louver geometry, D1 blocks air from intruding. Thus, D1 has the lowest velocity number, which is interesting.
And as a conclusion, this paper describes the development of a CFD simulation for use in analyzing the impacts of louver geometry and wind direction on cross-ventilation airflow in a generic isolated classroom. The simulation analyzed the 5 different wind directions and 5 different louver geometries to show the indoor air pattern. Based on the simulation of the generic isolated classroom, this study has 4 main conclusions. First of all, literature reviews shows that the computational model is validated to use wind tunnel measurement. Second, the internal airflow and air patterns show a very close and clear dependency to wind direction and louver geometry. Third, the best angle to optimum natural ventilation is 68°, which leaves the air in the deeper parts of the room. Hence, this can help to design the most efficient direction for getting lighter air. And the last but not least, the indoor air pattern shows that the model I1 has the most efficient air pattern for the classroom. Despite the assumption, the aerodynamic louver geometry decreases the airflow rate because it blocks the air entrance. This fact shows that first, using the industrial louver shape can be the most efficient option, both in case of energy and cost.
And in a final word, this study demonstrates that to what degree building simulation and energy modeling can change the design world. Software such as Computational Fluid Dynamics, Energy Plus, eQuest, Ecotech, Design Builder, and you name it, are the tools to create a better world and design ecological buildings for the future. Results that are determined by those softwares can help designers to look deep through the real function and performance of their design. The result of this research presents that shape, design, geometry, angle, direction, and dimension of louvers has substantial effect on the velocity, magnitude, pressure, and even temperature inside and outside of the building. Finding the best features to design an efficient louver for each window would improve operation of buildings. In fact, it could be the easy way to enhance usage of renewable energy and replace it with electricity or fossil fuel. Thank you so much for listening us. Have a great time.